So what you're probably wondering is the second derivative test that I had referred to earlier. So let's take a quick look at that before we move on to the next question. Second derivative test for checking critical numbers. Now, I'm not going to give you all the information on it yet, just because it'll make more sense when we start graphing, and you do get this formalized. But for now, it's just a rough way for us to save some time, particularly in applications. So if x equal a is a critical number for y equal f of x. So according to first derivative being equal to 0 or not defined, we find that a is a critical number. If the second derivative at a, so we plug that into the second derivative, we get a positive number greater than 0, then x equal a is a minimum. And if the second derivative is less than 0, then x equal a is a maximum. So don't think too hard about it yet. It'll make sense down the road. But here's how you remember it. If the second derivative is positive, then we draw a little happy face. And you see that that represents the minimum. So the positive I gives you that kind of doesn't look that happy the way I've got it drawn, but there you are. Whereas if the derivative is negative, then you got the scowl. And then that you can see represents a max. So you just draw these, then you'll have it. And it does come in handy. For the first example we didn't need it simply because it was giving us a closed interval so we could check the endpoints. But usually you don't have those closed intervals. So let's go on to this question with the diagram. A farmer wants to fence off corrals in the way that's shown below. Now this is a Math 20 question, by the way. It's not new. So you would have at some point dealt with these. And he has 1,200 meters total of fencing material. He wants to maximize the area. So I'm going to begin with this one by labeling the three sections, the vertical sections x, and then the horizontal ones y. And one thing to be aware of is for the total perimeter, it's going to be equal to 3x plus 2y. So in this case, we have 1,200 meters of perimeter of distance around it. It's equal to 3x plus 2y. And then what we do is note that we are trying to maximize the area. So area is equal to x times y. And if we're going to solve this question, we will probably have to get things in terms of one variable, which I'm going to express in terms of x. So the width is just equal to x. But the length, well, to get the length, we have to note that to isolate the y, we would go 1,200 minus 3x is equal to 2y. And then dividing by 2, we'd get 600 minus 3 over 2x. So therefore, the length can be expressed as 600 minus 3 over 2x. So we're set up. And in fact, we should be able to get an equation to represent the area by just multiplying that x by 600 minus 3 over 2x. You'll want to be aware of the domain. And not because the domain is going to have a big impact on this question, but it, although sometimes it does, but it does tell us how we can approach the question, whether we can just compare endpoints or not. See, this one, my argument would be that x has to be greater than 0. That x cannot be equal to 0 because that way you do not have a corral. And then the other point on this, because the width has to be greater than 0, the length also has to be greater than 0. So there has to be something to both sides. So 600 minus 3 over 2x must be greater than 0. And if you isolated this, x, negative 3 over 2x is greater than negative 600, and then divided out by that, the inequality will reverse. So 600 times 2/3 is 400. So in fact, the domain is going to be 0 is less than x, which is less than 400. Good idea to do this, even if it never comes into play. It just means that when we get an answer, if we got an x value bigger than 400, logically we couldn't work this question out. Now you'd probably find that eventually when you were solving for the y value, that if x was 400, all your material has gone into those three vertical sections. So be aware of that. But otherwise, our equation is going to be equal to x times 600 minus 3 over 2x. So the area is going to be 600x minus 3 over 2x squared. Now this is not a related rate, so we're not taking it with respect to time. So all we need to do is differentiate this. And now I'm just going to write this as a prime at x, and that's equal to 600 minus 3 over 2 times x squared is 3x. And I'll get a little bit more space to work, but really this is giving us the a very simple equation of which we now to find the critical numbers. So find critical numbers. So that would be where a prime at x is equal to 0. Or doesn't exist, but there's no place where it doesn't exist within that domain. So we just go 0 is equal to 600 minus 3x. Solve away, so 3x is equal to 600. And then x is equal to 200. So we got to find out, is this a minimum or a max? Now, realistically, it's pretty rare that there's any doubt about it. When the question asks you to minimize the cost, chances are you get your answer, particularly if there's one of them, then there's your answer. But I'm going to play it by the book. And I've already noted that a prime at x is equal to 600 minus 3x. So when I get the second derivative, that's what I'm going to do. I'm going to use the second derivative test. So the second derivative would be a double prime at x is equal to, well, negative 3. So this is interesting because we now substitute in our 200, and because there's no variable to work out, it means the second derivative at 200 is less than 0. So we draw the two negatives. That's going to give you this. So this is going to be a maximum area. So therefore, max area at x equal 200 meters. And then we want to get the dimensions, I suppose. So if x is equal to 200, to get the y value, well, you can do it either the formulas. Area is equal to LW. So, or actually, we have to use this one because this we don't have the total area yet. So 1200 is equal to 3x plus 2y. Actually, you could have gone to the 600 more easily, but whatever, I'm doing this one now, so I'll stick with it. So 1200 is equal to 3 times 200 plus 2y. So that's 600 subtracted away, so 600 is equal to 2y, so y is equal to 300. Or, as I said, or use y is equal to 600 minus 3 over 2 x, which would have made a little bit more sense. In any case, the dimensions will be x equal to 100 meters and y equal 300 meters. When you did these questions in Math 20, you didn't even pay any attention to the second derivative test because you knew you had a quadratic and you knew the behavior of the quadratic. So it seems like it's a little bit of overkill, but it really is just establishing good habits for more complicated equations. Just going to do one more, and then I'll do some more in the next lesson. So this is very similar, except instead of trying to maximize the area, if you read this question carefully, you're trying to minimize the cost of the fence. And you can see that you're only fencing 3 sides. So because we're trying to minimize the cost, what we're really trying to do is minimize the perimeter, the fencing, the part of the perimeter that's being fenced. And if you called these, just to keep things interesting, I'll go W and L. The perimeter is equal to 2W plus L. And we have these two variables again, and if possible, if we can express one in terms of the other, we can simplify this one. And we can, because the area is fixed at 720,000. That's equal to length times width. So if we express L in terms of W again, L is equal to area divided by W. So the 720,000 divided by W is equal to L. So the perimeter in terms of W, which was my choice to go W, you could have done the reverse. So 2W plus 720,000 over W. So in a better form, 2W plus 720,000 W to the negative 1. Before we get too carried away with this, check the domain out. And the domain, again, not stated really explicitly and probably not a big deal, but it's safe to say that the width has to be something. So the width has to be greater than 0. And then, with the regards to the other part, the length, if you have a few ways you can probably tackle this one, but if the total area is 720,000 and divide that by what we've got, W equals 0, you see that you really don't, mathematically, there's no restriction on what the length can be. As long as the W is not equal to 0, in theory, you can have infinite length. So there is no upper limit on this. So you can reason your way to it in a couple ways, and it's going to become a very narrow type of rectangle, but in theory, it could work that way. So all we need to worry about then is W being greater than 0. There's no obvious other restriction. So now we just go further. We get the derivative, so P prime of W is equal to 2 minus 720,000, and then W to the negative 2, subtract 1. So therefore the derivative will be 2 minus 720,123 over W squared. And we want to get the critical numbers. So I'm going to get some more space. But the critical numbers So P prime at W equals 0. First off, so 0 is equal to 2 minus 720,000 over W squared. Now, what I've encouraged everybody to do up till now is get a common denominator and express it like that. And that's a good way to do it. But I'm going to cheat, because I don't want to do first derivative analysis. All I'm going to do is bring the 720,000. It's not really cheating, but over W squared is equal to 2. So 2W squared is equal to 720,000. Divide by 2, and you'll get 360,000. So then take the square root. Now you cannot have the negative value with this one. So we can do both, but we'll have to adjust our answer. So plus or minus 600. So therefore W is equal to 600 meters. And no critical numbers where this is equal to 0, because W, the denominator is not within, where W equals 0, that's not within the domain. So no critical numbers where P prime at W doesn't exist. So the question then, is this a min or a max? To answer that little question, we then consider that P prime at W is equal to 2 minus 720,000 W squared. So the second derivative is equal to negative, so it's 720,000 times 2. Make sure you get the zeros all down. So negative 1440000. And then, oh, hang on. Excuse me, because that is W to the negative 2, so that's going to become positive. It's late in the day for me, by the way, in case you haven't been able to figure that out. So W to the negative 3. So the second derivative is 1,440,000 over W cubed. So when we plug in our value of 600, we don't need a number. We just need to know whether or not it's positive or negative. And in this case, it seems clear to me that it's going to be a positive number. So positive, positive, well, that's going to produce a minimum. So therefore, W equals 600 meters produces a minimum. And make sure you answer the question. We want to get the dimensions, so to get the length, we are aware that the length would be equal to the area divided by the width. So the length would be equal to 720,000 divided by 600. So divide that out, and you get 1,200. So L is equal to 1,200 meters. So then, the dimensions should be W equals 600 meters and L equal 1,200 meters. So I'll stop there, and then I will in the next lesson do a few more others type problems. Thank you for your time.